All right, let's talk about 5.4. This is the sum and difference identities for sine and cosine. Okay, so it's going to be these two, right? So the sum and difference identities for sine, and then the sum and difference identities for tangent. Sorry, I think I said cosine a second ago, but I meant tangent. Okay, we did cosine in the previous section. So to prove these identities is just a matter of applying what we know about the sum and difference identities for cosine from the previous section. So sine of a plus b is sine a cosine b plus cosine a sine b. And here's a proof of that fact, right? So notice that sine of a plus b is cosine of 90 degrees minus a plus b. That's just using that cofunction identity. Okay, and then we can distribute that negative sign and regroup. So this is 90 degrees minus a and then minus b. And then we can apply the difference identity for cosine, right? So cosine of 90 degrees minus a minus b is cosine of 90 degrees minus a cosine of b plus sine of 90 degrees minus a sine of b. And then we use cofunction identities again to call this sine and call this cosine, right? And that proves the statement. You could go through a similar line of reasoning to show that sine of a minus b is sine a cosine b minus cosine a sine b. And actually, what you could do is use this fact, right? And just call this a plus negative b, and that would be another way to prove it. So I'm not going to go through the proof of that one. It's pretty easy to prove once you have this other fact in hand. Same thing goes for tangent, because tangent's just sine over cosine, right? So so potentially, you could prove these things pretty easily since you already know what sine of a plus b and cosine of a plus b are. When you just divide those two, and you'll end up here, right? Same thing with tangent of a minus b. So these are the two identities for tangent: the sum identity and the difference identity. One thing that I'll point out to you, if you look at your formula sheet, be careful with the minuses and pluses, right? So for the sine of alpha plus beta identity, notice that the signs stay the same. So it's plus, plus, minus, minus. So the pluses are both on top, the minuses are both on bottom. And so the way that you read that is sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. But sine alpha minus beta would be sine alpha cosine beta minus cosine alpha sine beta. Now contrast that with the cosine identities, right? So here the signs switch. So if you have a cosine alpha plus beta, then you're going to use a minus sign on the right hand side. If you have a cosine alpha minus beta, then you'd have a plus sign on the right hand side. Okay, and then the same thing goes for tangent. So be very careful, right? So it's a plus minus here, a plus minus there. So the sign in the numerator stays the same, but in the denominator it's a minus plus. So in the denominator the sign changes. Okay, so just be careful of that. And let's go through several examples. So now that we've seen those formulas, I've got how many? 1, 2, 3, 4, 5, 6, 7. I think I've got 9 examples to show you. Okay, so here we go. And these are all pretty similar to the kinds of examples that we did in the previous section, right? So we can find the exact value of something like sine of 7 pi over 12, right? What you need to do is think of two angles, right? Because we don't know sine of 7 pi over 12 off the top of our heads, but we do know angles like, pi over 4, pi over 6, pi over 3, pi over 2, etc. So what you need to do is try to think of two angles whose sine values you know, okay, whose sum or difference is 7 pi over 12. So give the video a pause, see if you can figure that out. Okay, so let's think about this. Pi over 3 would be 4 pi over 12, and pi over 4 would be 3 pi over 12. So I think 7 pi over 12 is just pi over 3 plus pi over 4, right? So I'm going to write this as sine of pi over 3 plus pi over 4, right? You get common denominators. This is going to be, here you would multiply by 4 pi over 12. Here you'd multiply by 3 pi over 12, right? 7 pi over 12. Okay, and now I can apply the sum formula for the sine function to call this. So for the sine function, it's sine A cosine B plus cosine A sine B. Okay? And then the rest of this we can do in our heads, right? Sine pi over 3. So sine of pi over 3 is root 3 over 2. Cosine pi over 4 is root 2 over 2. Cosine pi over 3 is 1/2. And sine of pi over 4 is root 2 over 2. So this is root 6 over 4 plus root 2 over 4. We always end up with the same kinds of answers on these problems. But anyway, there's the exact value. Okay, here's another one. See if you can do the same thing for tangent of 15 degrees. Okay, I think the math is a little bit easier when you're working with degrees, because you don't have to get common denominators and things like that. For 15 degrees, I think we have a couple of options. We could do 45 minus 30, or we could do 60 minus 45, right? Either way, you'll get the same answer. I'm going to do, I'll do the first way. Okay, and so now I'm going to apply my formula. Tangent 45 minus 30, that's going to be tangent of A minus tangent of B divided by 1 plus tangent of A times tangent of B. Okay, and let's see what we get. So tangent 45 degrees is 1. Tangent 30 degrees, oh, I always have to think of these, right? So tangent 30 degrees would be 1/2 divided by root 3 over 2. So that's going to be 1 over root 3. Or if you like, you could rationalize it and call it root 3 over 3. And in the denominator, we're going to have 1 plus 1 times, again, root 3 over 3. Okay. So first of all, I'm going to clear everything by multiplying by 3 in the numerator and denominator here. So I'm going to clear those complex fractions. And we get 3 minus root 3 over, it looks like it's going to be 3 plus root 3. And there you go. I mean, to rationalize that, you'd have to multiply by the conjugate and stuff, which may not end up terribly bad, but I'm just going to leave the answer that way, though. I don't know. To make your answer match the answer in the back of the book, you might have to rationalize it. So I'd be okay with this on a test or a quiz, but just to remind you how rationalizing works. So you want to multiply by the conjugate of the denominator to clear all of the radicals in the denominator. Okay. And if you do that, then you get 9 minus 3 root 3 minus 3 root 3, so that's going to be minus 6 root 3, and then plus 3 over 9 minus 3 root 3 plus 3 root 3 cancels, and then minus 3. So this is going to be 9 plus 3 is 12 minus 6 root 3 over 9 minus 3 is 6. Ooh, actually that ends up pretty nice, doesn't it? Because now you can simplify by 6 and you just end up with 2 minus square root of 3. which I would imagine is the answer your like if you have a nice enough calculator, that's probably the answer your calculator will give you. Let me see. Curious. So tangent of 15 degrees. Yeah. I mean, mine gives it to me kind of in this weird way, but if you distribute that negative sign, then it's a negative root 3 plus 2, which is exactly what we've got here. So, anyway, whoops. So that's kind of nice. Let's look at another set of examples. Okay. So let's write each function let's write each function as an expression involving functions of theta alone. Okay, so we don't want like theta over 2 or 2 times theta or anything like that. We just want theta by itself. So let's do this for tangent of 45 degrees plus theta. You can probably guess what you're going to have to do here, right? So go ahead and pause the video and see if you can work that out. Okay, here's my solution. So tangent of 45 degrees plus theta is going to be tangent 45 degrees plus tangent theta divided by 1 minus tangent of 45 degrees times tangent of theta. And from there we just simplify, right? Tangent 45 is 1. So we end up with 1 plus tangent theta over 1 minus tangent theta. I don't know, based on our previous example, you might want to like multiply by the conjugate of that and see what you end up with. I'm just going to leave my answer that way though. But if you multiply by like 1 plus tangent theta, you might end up with something kind of nice. In fact, well, I'm going to leave it. I'm going to leave it that way. Let's do another one. Let's do sine of 60 degrees minus theta. Okay, go ahead and give it a pause, see if you can work that one out. Okay, here I go. This is going to be sine 60 cosine theta minus cosine 60 sine theta. Okay. Sine 60 is root 3 over 2. Cosine 60 is 1/2. And that's that, right? We've achieved our goal. Okay. Here's another one. Another set of examples. So let's suppose that sine S is 3/5. Sine T is negative 12/13. And S is in quadrant 1. T is in quadrant 3. And then let's find sine of S plus T. Okay, so you can see these are all kind of similar problems to the sort of things that we were doing yesterday. And if you remember, well, yesterday, I mean in the previous section, right? And if you remember in the previous section, this was kind of a long problem. Let's see if we can work it out, right? So obviously we're going to use the sum formula for sine. So sine S plus T is sine S cosine T plus cosine S sine T. I wish they would use different letters than S and T because S starts to get confusing. But anyway, okay, so there's the sum formula. So what do we need in order to complete this problem? We need to know sine S, which we've got. We need to know cosine t, which we don't have. We need to know cosine s, which we don't have. And we need to know sine t, which we do have. So I think we should try to find cosine t. We should try to find cosine t and cosine s before we do anything else. So you could do that by, making little right triangles or whatever, or by applying a Pythagorean identity. In the previous section, I did this by using Pythagorean identities. Let's do it this time by drawing right triangles. Just remember, you've got to get the angles in the correct quadrant, though, in order to correctly label whether you should take the positive or the negative square root. So for cosine t, t is in quadrant 3. Right, so there's t. And let's see, sine t is negative 12/13. So if I draw my little right triangle now, sine t is opposite, so that should be a negative 12 since I'm down here in quadrant 3 over 13. And then you can use Pythagorean theorem to solve for this missing side. So you would say, x squared plus negative 12 squared equals 13 squared. And when you do all of that, you're going to get 5. You're going to get 5. Well, what you'll get is actually plus or minus 5. So you have to choose whether it's going to be positive or negative 5. It should be negative because you're here in quadrant 3, right? X is negative over here. Okay? So that'll tell us what cosine t is, right? Cosine t is negative 5/13. Okay, so that's t. And what about s? S is in quadrant 1. So there's s. We could draw a little right triangle. Sine s is 3/5. Again, that's opposite over hypotenuse. This time it's a positive 3 because y is positive in quadrant 1. And again, you can use Pythagorean theorem to solve for the missing side. You should get 4. And it should be a positive 4 this time because, again, x is positive when you're in quadrant 1. All right. So with that in mind, now we can fill in all of this stuff, right? Sine s is 3/5. Cosine t, so here's t, right? Cosine t is adjacent over hypotenuse, negative 5/13. Okay, so there's sine s cosine t plus cosine s. So here's s. Cosine s would be 4/5 times sine of t, which we were given as negative 12/13. So part of me is tempted to cross-cancel 5s here before I multiply, but I can't cross-cancel on this term, and I'm going to want to add these two things together, which means I'm going to need a common denominator anyway, so I might as well not cross-cancel that 5 yet and just multiply it out the way it is. So I'm going to have negative 15 over 5 times 13 should be 75. Ooh, let me check. 5 times 13. 65. Ooh, good thing I checked, right? 65. And then 4 times negative 12 is negative 48 over 65. Negative 15 minus 48 is negative 63. So you get negative 63/65. Okay. So there's that one. Part B now. Part B, let's do tangent of s plus t. Alright, same scenario as before. Let's do tangent of s plus t. Well, you know sine of s plus t. I suppose one thing that you could do is figure out what cosine of s plus t is, and then just divide those two answers, and that would be tangent of s plus t. But we also have a formula for tangent of s plus t. We might as well use it, right? This is going to be tan s plus tan t over 1 minus tan s tan t. And figuring out tangent of s and t is pretty easy because we've got these little triangles that we've already done. We know that tangent's just opposite over adjacent, right? So tangent s, here's s over here. So opposite 3 over adjacent 4. So tangent s is 3/4. Tangent t, opposite over adjacent, that's negative 12 over negative 5. Or in other words, just 12/5, okay, over 1 minus tangent S times tangent T. And the rest is history, right? So yeah, so the rest is just multiplying by the common denominator. I think if I multiply numerator and denominator by 20 because that's the LCD of 4 and 5, right? So that's all of my little denominators. So I'm just going to go ahead and clear all of these fractions by multiplying by 20 over 20. And what do we get? So when I distribute here, the 4 will cancel the 4 and leave a 5. 5 times 3 is 15. Here the 5 will cancel 5 and leave a 4. 4 times 12 is 48. In the denominator, 20 times 1 is of course 20. And then when I distribute to this term here, the 4, I mean, imagine that I'd multiplied it out, right? I've got 3 times 12 is 36, 36 over 20. Well, when I multiply by 20, that's just going to be 36, right? Okay. Very good. 15 plus 48. Well, 48 plus 5 is 53, so plus 10 is 63. And 20 minus 36 is negative 16. Ooh, so negative 63/16 should be the answer there. That doesn't simplify. That's kind of disappointing, but there you go. Sometimes life is that way, right? But anyway, so so one more little task here. Let's find the quadrant of S plus T. So let's see if we can find, right? So find the quadrant of S plus T. Well, looking at our previous problems, sine and tangent are both negative. And where does that happen? It doesn't happen in quadrant 1. They're both positive there. In quadrant 2, sine is positive, so it's not quadrant 2. In quadrant 3, sine is negative, but tangent is positive, right? And in quadrant 4, sine is negative and tangent is also negative, so it must be quadrant 4. Okay, and that's all there is to that one. Okay, so one more set of problems. Let's practice verifying some more identities. Okay, let's do sine x plus y plus sine x minus y equals 2 sine x cosine y. I'll let you give the video a pause and see if you can work that one out. Okay, here I go. I'm just going to use the sum and difference formulas for these two things. Sine x plus y should be sine x cosine y plus cosine x sine y. Okay, so that's just, like, this whole thing is just that first one there. And then sine x minus y should be sine x cosine y minus cosine x sine y. Okay, so this whole thing is that second one. Alright. Well, look at that, right? Cosine x sine y minus cosine x sine y, those are going to cancel. And you're going to get, oh, and then here you have like terms, right? Sine x cosine y plus sine x cosine y, that's just 2 sine x cosine y. How boring, right? We got there in 2 steps. So that one was easy. Here's another one. Let's do sine s plus t over cosine s cosine t equals tangent s plus tangent t. Okay, so I'll let you pause that one and give it a try. Okay, so here I go. This is interesting because this almost looks like tangent of s plus t. It's just that we're missing the denominator, the 1 minus tangent s tangent t. I suppose you might do something with that, but I think maybe a more obvious place to start is to use the sum formula up here to break that apart. So that's what I'm going to do. So sine s plus t is sine s cosine t plus cosine s sine t. You see why the s's are confusing, man. Okay, and then divided by cosine s cosine t. Now what do we do with that? Well, we can split the sum. When the sum is in the numerator, you can split it like this. Sine s cosine t over cosine s cosine t plus cosine s sine t over cosine s cosine t. Right? That's perfectly valid, because if you were to go backwards and add these things, they already have a common denominator, so you just add the numerators and you end up right back here. Be careful though, this is not true of the denominator, right? So like, you know, a over b plus c is not a over b plus a over c, right? It doesn't work that way, right? It is true that a plus b over c is a over c plus b over c, right? That's true. And that's what we just used. But this is not, this one right here is not true. But anyway, this is perfectly legal. Now the cosine t's will cancel on that first term. We'll be left with sine s over cosine s. And the cosine s's will cancel on the second term. We'll be left with sine t over cosine t. Oh, there it is, right? Tangent s, tangent t. How boring. But there's that one. Okay, so those are all the examples that I had for this section.